Imagine a place where time itself stops moving, where light cannot escape, where the very fabric of space is torn apart like paper in a storm. Imagine a monster so powerful that it devours entire stars for breakfast, massive that millions of suns combined would pale in comparison, so mysterious that even the greatest minds in human history have struggled to understand its true nature. These cosmic predators lurk in the darkness of space, invisible yet undeniable, silent yet screaming with gravitational fury. They are the ultimate destroyers and the ultimate creators, the ending of everything and perhaps the beginning of something new. They have haunted our imaginations, challenged our understanding of reality, and forced us to question everything we thought we knew about the universe. They are black holes, and their story is the most incredible tale ever written in the cosmos itself. From the moment the first star collapsed billions of years ago to the groundbreaking photograph captured just a few years ago, black holes have been the universe's greatest mystery and most terrifying wonder. They sit at the hearts of galaxies, controlling the dance of billions of stars. They bend the laws of physics until those laws scream for mercy. They hold secrets about the birth of the universe, the nature of time, and perhaps even the key to understanding dimensions beyond our imagination. Scientists have dedicated their entire lives to studying these cosmic enigmas. Explorers have pointed telescopes toward the heavens hoping to catch just a glimpse of their shadow. Dreamers have wondered what lies beyond the point of no return, that ultimate boundary called the event horizon where everything changes forever. This is not just a story about objects in space. This is a story about humanity's quest to understand the impossible, to see the invisible, to explain the unexplainable. This is a story about brilliant minds who dared to imagine what others said could not exist. This is a story about mathematics that predicted reality before reality revealed itself. This is a story about courage, curiosity, and the unstoppable human desire to know what lies in the darkest corners of existence. This is the entire story of black holes, from their violent births to their mysterious deaths, from ancient questions to modern discoveries, from pure theory to stunning photographs that changed everything we thought we knew. Prepare yourself for a journey into darkness, into mystery, into the very edge of human understanding. Prepare yourself to witness the most powerful force in all of creation. Long before anyone imagined black holes, long before telescopes pierced the night sky, long before science itself was born, humans looked upward and wondered. They saw the stars scattered across the darkness like diamonds on velvet cloth. They noticed patterns in the heavens, movements that repeated night after night, season after season. They created stories to explain what they saw, tales of gods and monsters, heroes and journeys written in constellations. But beneath the mythology, beneath the ancient wonder, there lived deeper questions that would echo through thousands of years. What are stars made of? How far away do they sit? What keeps them burning in the endless night? And perhaps most haunting of all, what happens when they die? The ancient Greeks were among the first to try answering these questions with reason rather than myth. Philosophers like Aristotle believed the heavens were perfect and unchanging, made of special celestial material that never aged or altered. They thought stars were fixed to crystal spheres that rotated around the earth, creating the movements they observed each night. This view dominated human thinking for nearly 2,000 years, accepted as truth by scholars and common people alike. But even then, curious minds wondered about the nature of light itself. Why does light travel? What carries it from the sun to our eyes? These questions seemed simple, but contained mysteries that would take centuries to unravel. In ancient India, mathematicians and astronomers developed incredibly sophisticated understanding of celestial movements. They calculated the sizes of planets and distances to the moon with remarkable accuracy. They understood that eclipses followed predictable patterns and that the universe operated according to natural laws rather than divine whims. Chinese astronomers kept detailed records of everything in the sky, documenting comets, meteors, and even exploding stars called supernovas. These ancient observers noticed that sometimes new stars would appear where none had been before, shining brilliantly for weeks or months before fading away. They did not know they were witnessing the deaths of massive stars, the very events that would eventually create black holes. Islamic scholars during the medieval period preserved and expanded upon ancient knowledge when much of Europe had forgotten it. They built observatories, refined mathematical tools, and asked ever deeper questions about the nature of reality. They wondered whether the universe was infinite or finite, whether time had a beginning or stretched backward forever. They debated whether empty space was truly empty or filled with some invisible substance. These philosophical and scientific discussions laid groundwork for future discoveries, even though the scholars themselves could never have imagined where their questions would lead. By the time of the Renaissance, European thinkers began challenging ancient authorities and looking at the heavens with fresh eyes. Copernicus dared to suggest that Earth was not the center of everything, that instead we orbit the sun along with other planets. This revolutionary idea shook the foundations of human understanding. If Earth was not special, if we occupied no privileged position in the cosmos, then what did that mean about our place in creation? Galileo turned newly invented telescopes skyward and discovered mountains on the moon, spots on the sun, and moons orbiting Jupiter. Each discovery chipped away at the old certainties, revealing a universe far stranger and more wonderful than anyone had imagined. But even as astronomy advanced, even as humans mapped the visible universe with increasing precision, no one yet conceived of objects so dense and dark that light itself could not escape. The tools needed to imagine such things did not exist. The mathematics remained undiscovered. The physics lay hidden, waiting for brilliant minds to uncover them. The story of black holes could not truly begin until humans understood what light really was, how gravity actually worked, and what stars were made of. Those revelations would come, but first science needed to mature, to develop the language and concepts necessary to describe the ultimate darkness lurking in the cosmic deep. The journey toward understanding black holes required first understanding two fundamental forces of nature, light and gravity. For most of human history, these phenomena seemed completely separate, unrelated aspects of reality. Light was something that allowed us to see, that came from the sun and fire and stars. Gravity was the force that made things fall, that kept our feet on the ground and the moon in the sky. No one suspected these two forces would eventually become intertwined in ways that would reveal the existence of the universe's strangest objects. Isaac Newton revolutionized science in the late 1600s by describing gravity with mathematical precision. He realized that the same force pulling apples to the ground also kept planets orbiting the sun. He showed that gravity was universal, acting between all objects with mass, whether tiny pebbles or massive stars. His equations could predict planetary motion with stunning accuracy, allowing astronomers to chart the heavens with confidence. Newton imagined gravity as a force that instantly across space, somehow reaching from the sun to Earth without any medium carrying it. This bothered Newton himself, but his mathematics worked so well that scientists accepted this mysterious action at a distance. Newton also studied light extensively, conducting experiments with prisms that split white light into rainbow colors. He believed light consisted of tiny particles he called corpuscles that traveled in straight lines at enormous speed. Other scientists disagreed, arguing that light behaved like waves moving through some invisible medium called the luminiferous ether. Debates raged for decades about light's true nature. Meanwhile, Newton's theory of gravity reigned supreme, seemingly perfect and complete. Scientists used his equations to discover new planets, predict eclipses, and understand the motion of everything from comets to galaxies. But as the 1800s progressed, careful experiments began revealing cracks in the Newtonian worldview. Scientists measured the speed of light and found it always traveled at the same velocity regardless of how the observer moved. This seemed impossible according to common sense. If you run toward something moving toward you, the relative speed should increase. But light did not behave this way. It always moved at the same speed no matter what. This strange fact puzzled physicists and suggested something fundamental about reality remained misunderstood. James Clerk Maxwell unified electricity and magnetism into a single theory in the mid-1800s, showing they were two aspects of the same electromagnetic force. His equations revealed that light itself was an electromagnetic wave, oscillations of electric and magnetic fields propagating through space. Maxwell's theory predicted light's speed with perfect accuracy, but it also raised troubling questions. If light was a wave, what medium carried it? Water waves need water, sound waves need air. So what carried light waves through the vacuum of space? Scientists proposed the luminiferous ether, an invisible substance filling all of space, but experiments failed to detect it. The crisis in physics deepened as scientists realized Newton's gravity could not fully explain certain observations. The planet Mercury's orbit showed tiny deviations from what Newton's equations predicted. Something was wrong, but what? Meanwhile, philosophical problems lurked within Newton's framework. How could gravity act instantly across vast distances? What mechanism allowed the sun to grip Earth from 93 million miles away? Newton himself had admitted he could not explain it, famously writing that he would not feign hypotheses about the ultimate cause of gravity. He simply described how it worked mathematically without claiming to know why. As the 19th century closed and the 20th century dawned, physics stood at a crossroads. The old certainties no longer seemed so certain. Light behaved in ways that made no sense according to classical physics. Gravity worked perfectly for most situations but showed mysterious problems at the edges. Scientists felt they were close to understanding everything, yet the most important questions remained unanswered. The stage was set for a revolution that would transform human understanding of space, time, and gravity itself. That revolution would come from a young man working in a patent office in Switzerland, someone whose name would become synonymous with genius itself. Albert Einstein did not set out to predict black holes. He simply wanted to understand how the universe really worked. Born in Germany in 1879, Einstein showed early brilliance in mathematics and physics, but struggled with formal education's rigid structure. He asked questions that annoyed his teachers, challenged accepted wisdom, and thought deeply about problems that fascinated him. After graduating, he could not find an academic position and took a job at the Swiss Patent Office in Bern, evaluating applications for new inventions. But in his spare time, he pondered the deepest questions in physics, working through problems that stumped the greatest minds of his era. In 1905, Einstein published 4 papers that changed physics forever. One explained the photoelectric effect, showing that light sometimes moves particles, not waves. Another proved that atoms really existed by explaining how tiny particles suspended in liquid move randomly. A third introduced the special theory of relativity, which revolutionized understanding of space and time. And the fourth contained the most famous equation in history, E=mc², showing that mass and energy were different forms of the same thing. These papers came from a 26-year-old patent clerk with no laboratory, no research funding, no academic position, just pure thought, mathematical brilliance, and the courage to follow logic wherever it led. The special theory of relativity solved the mystery of light's constant speed by showing that space and time themselves were not absolute and unchanging as everyone had assumed. Instead, they were flexible and relative, depending on how fast you moved. Time could slow down, distances could shrink, and events that seemed simultaneous to one observer might happen at different times for another observer moving at different speed. This sounded insane, contradicting every intuition humans had developed through millions of years of evolution. But Einstein showed that if you accepted the experimental fact that light's speed never changes, then these strange consequences followed logically and inevitably. Special relativity worked beautifully for objects moving at constant speeds, but it did not address gravity or acceleration. Einstein spent the next 10 years wrestling with these problems, trying to incorporate gravity into his new framework. He experienced what he later called the happiest thought of his life, while sitting in his patent office chair. He imagined someone falling from a roof and realized that during the fall, they would feel weightless, as if gravity had disappeared. This simple insight opened a door to profound understanding. Einstein realized that gravity and acceleration were deeply connected, perhaps 2 aspects of the same phenomenon. Someone standing in a closed room could not tell the difference between gravity pulling them down and the room accelerating upward through space. This principle of equivalence became the foundation for his general theory of relativity. But Einstein went further, making an intellectual leap that ranks among the greatest achievements in human history. He proposed that gravity was not a force at all in the traditional sense. Instead, massive objects like stars and planets curved the very fabric of space and time around them. Objects moving through this curved spacetime followed the curves, which we perceive as gravitational attraction. Imagine space as a rubber sheet stretched flat. Place a heavy ball in the center and the sheet curves, creating a depression. Now roll a smaller ball across the sheet. It will curve toward the heavy ball, not because any force pulls it, but because the sheet itself is curved. Einstein showed that the universe works similarly, except in 4 dimensions including time, and the curvature affects not just the path objects take, but also how time itself flows. Near massive objects, time actually runs slower. Clocks tick at different rates depending on how deep they sit in a gravitational well. Einstein published his general theory of relativity in 1915, presenting equations that described how mass and energy curve space-time, and how that curvature creates what we call gravity. These equations were fearsomely complex, so difficult that even Einstein struggled to find solutions to them. But they made predictions that differed from Newton's theory in subtle ways that could be tested. One prediction was that light itself would bend when passing near massive objects because it followed the curves in space-time. Starlight grazing past the sun should shift position slightly, something that could be observed during a solar eclipse when the sun's glare did not overwhelm the stars. In 1919, British astronomer Arthur Eddington led expeditions to a solar eclipse and measure the positions of stars near the sun. When he announced that his measurements matched Einstein's predictions, the world erupted in excitement. Einstein became an international celebrity overnight, his theory confirmed by nature itself. Headlines proclaimed that Newton had been overthrown, that a new understanding of the universe had emerged. But buried within Einstein's complex equations lay implications that even Einstein himself found difficult to accept. The mathematics suggested that under certain extreme conditions, space-time could curve so severely that it would collapse into an infinitely dense point from which nothing, not even light, could escape. These solutions seemed like mathematical curiosities, abstract impossibilities that surely could not exist in the real universe. Yet they were the first theoretical hints that black holes might be possible. Just months after Einstein published his general theory of relativity, while World War I still raged across Europe, a German physicist named Karl Schwarzschild achieved something remarkable. Serving as a soldier on the Russian front, suffering from a painful autoimmune disease, Schwarzschild found the focus to work on Einstein's equations. He looked for exact mathematical solutions that would describe the space-time around a perfectly spherical, non-rotating, massive object. Most scientists assumed Einstein's equations were too complicated to solve exactly, but Schwarzschild succeeded where others had not even tried. The Schwarzschild solution revealed something strange and troubling. The equations showed that if you compressed enough mass into a small enough region, something extraordinary would happen. There existed a critical radius now called the Schwarzschild radius. Space-time would curve so severely that it would form a boundary of no return. Anything crossing this boundary could never escape, not even light traveling at its maximum speed. Inside this radius, all paths through space-time would lead inward toward an infinitely dense point at the center. A singularity where the equations themselves broke down and predicted infinite density and infinite curvature. For a mass like the Sun, Schwarzschild calculated this critical radius would be about 3 kilometers. For Earth, it would be less than a centimeter. These numbers seemed absurd and purely theoretical. How could you possibly compress the entire Sun down to a ball just 6 kilometers across? The forces required seemed impossible. The temperatures and pressures would exceed anything imaginable. Everyone, including Einstein himself, assumed these mathematical solutions represented interesting abstractions but not physical reality. The universe surely would not permit such extreme conditions to actually occur. Schwarzschild sent his solution to Einstein, who was amazed by the mathematical achievement but also troubled by its implications. Einstein published Schwarzschild's work, ensuring it reached the scientific community, but privately he doubted such objects could really exist. Tragically, Schwarzschild died just months later in 1916, knowing that his solution would become the foundation for understanding some of the universe's most important objects. His name would become forever attached to the concept of the event horizon, that boundary beyond which events can never be observed from the outside universe. For the next several decades, most physicists treated the Schwarzschild solution as a mathematical oddity rather than a description of something real. They focused on testing other predictions of general relativity, measuring how gravity bent light, how time slowed near massive objects, how Mercury's orbit deviated from Newtonian predictions. These tests confirmed Einstein's theory beautifully, but the extreme case of complete gravitational collapse seemed like science fiction. The mathematics said it could happen, but surely nature had ways of preventing such bizarre outcomes. A few scientists, however, began wondering what would actually happen if you watched a star collapse into a Schwarzschild object. They worked through the mathematics and discovered something even stranger than anyone had imagined. From the perspective of someone falling toward the Schwarzschild radius, everything would seem normal. You would cross that boundary without feeling anything special happen at that precise moment. But from the perspective of someone watching from far away, something incredible would occur. As the falling observer approached Schwarzschild radius, they would appear to slow down. Light from them would become increasingly red-shifted, stretched toward longer wavelengths. Time itself would appear to slow for them as measured by distant observers. They would seem to freeze at the edge of the boundary, never quite crossing it, their image fading and reddening until it disappeared entirely. This bizarre prediction suggested that these objects would appear completely black to outside observers, because light could not escape from inside the boundary, and even light from just outside would be stretched to invisibility. They would be invisible gravitational traps, detectable only by effects on surrounding matter and space. But still, most scientists assumed the universe would never actually create such things. They thought that stars might collapse somewhat under their own gravity, but would always be held up by some force, some pressure that would prevent the ultimate catastrophe of complete collapse. Those comfortable assumptions would not survive the next wave of discoveries about how stars actually work and what happens when they die. To understand why black holes exist, we must first understand what stars are and how they live and die. For thousands of years, stars seemed eternal and unchanging, distant lights that would shine forever. But in the early 20th century, scientists began unraveling the truth. Stars are not eternal. They are born, live millions or billions of years, and eventually they die. And how they die depends entirely on how massive they are when they form. Stars form from vast clouds of gas and dust floating in space, mostly hydrogen left over from the Big Bang. When a cloud becomes dense enough, gravity begins pulling it together. As it contracts, the center heats up. Eventually, the core becomes so hot and dense that hydrogen atoms begin fusing together, combining to form helium. This nuclear fusion releases enormous energy, creating the light and heat that makes stars shine. The outward pressure from this energy production balances the inward pull of gravity, and the star becomes stable. For most of its life, a star exists in this balance, steadily converting hydrogen to helium in its core. Scientists learned that stars come in many sizes. The smallest ones contain just 8% as much mass as our Sun, barely hot enough to sustain fusion. The largest stars contain more than 100 times the Sun's mass, burning brilliantly but briefly. Our own Sun sits comfortably in the middle, average in almost every way. It has burned steadily for about 4.6 billion years and will continue for about another 5 billion years before its hydrogen fuel begins running out. What happens when a star exhausts its fuel depends dramatically on its mass. For stars similar to our Sun, the end comes relatively gently. When the core runs out of hydrogen, fusion stops and gravity causes the core to contract. This contraction heats the core, eventually becoming hot enough to fuse helium into heavier elements like carbon and oxygen. The outer layers of the star expand enormously, creating a red giant. Eventually, these outer layers drift away into space as a beautiful planetary nebula, while the core remains as a dense object called a white dwarf. A white dwarf is incredibly dense, packing about the Sun's entire mass into an object about the size of Earth. But it generates new energy. It simply cools slowly over trillions of years. White dwarfs are held up against further collapse by a quantum mechanical effect called electron degeneracy pressure. Electrons resist being squeezed too closely together because of the Pauli exclusion principle, which states that two electrons cannot occupy the same quantum state. This creates an outward pressure that balances gravity, preventing further collapse. The star has reached a stable final state, slowly fading but never collapsing further. This will be our Sun's fate, and the fate of most stars in the universe. But in the 1930s, an Indian astrophysicist named Subramanian Chandrasekhar made a disturbing discovery. He calculated that electron degeneracy pressure could only support a white dwarf up to a certain mass limit, about 1.4 times the Sun's mass. Above this Chandrasekhar limit, gravity would overwhelm the electron pressure and the star would have to collapse further. But collapse into what? What could possibly stop it? Chandrasekhar presented his findings to the scientific community and faced harsh criticism, particularly from British astronomer Arthur Eddington, the same man who had confirmed Einstein's theory during the eclipse expedition. Eddington simply could not accept that it would permit of such catastrophic collapse. He believed some unknown force must exist to prevent it. He used his considerable authority to dismiss Chandrasekhar's work, causing the young scientist great distress. But Chandrasekhar was correct, and eventually the scientific community recognized his brilliance. He would later win the Nobel Prize for his discoveries about stellar evolution. For massive stars, those born with more than about 8 times the Sun's mass, death comes much more dramatically. These stars burn through their fuel much faster than smaller stars, living only millions of years instead of billions. When they exhaust the hydrogen in their cores, they begin fusing helium to heavier elements. Then they fuse those elements into even heavier ones. The star becomes like an onion, with layers of different elements undergoing fusion at different depths. Iron accumulates at the very center, but iron is special. Fusing iron consumes energy rather than releasing it. When the core becomes mostly iron, fusion stops and there is no longer any outward pressure to resist gravity. What happens next occurs in less than a second. The core collapses catastrophically, falling inward at nearly a quarter the speed of light. Electrons are forced into atomic nuclei, combining with protons to form neutrons. The core becomes a ball of pure neutrons, packing more than the Sun's entire mass into a sphere just 20 kilometers across, far denser than any white dwarf. The density becomes so extreme that a teaspoon of neutron star material would weigh more than 1 billion tons on Earth. The collapse stops abruptly when the neutrons reach nuclear density, when they literally touch each other with no empty space between them. The infalling outer layers bounce off this incompressible core and explode outward as a supernova, one of the most powerful explosions in the universe, briefly outshining entire galaxies. These discoveries about stellar death revealed that the universe could create objects far denser than anyone had imagined. White dwarfs and neutron stars were not theoretical curiosities. They were the actual corpses of dead stars scattered throughout the galaxy. But the most important question remained unanswered. What happened to stars so massive that even neutron degeneracy pressure could not stop their collapse? The mathematics of general relativity insisted such stars must collapse all the way down to a singularity, creating what we now call black holes. But did nature really permit this ultimate catastrophe? Or did some unknown force always prevent it? Scientists would debate this question for decades, even as evidence slowly accumulated that the universe did indeed create these impossible objects. Throughout the 1930s and 40s, physicists grappled with bizarre implications of general relativity's predictions about stellar collapse. The mathematics seemed clear. If enough mass collapsed into a small enough region, nothing could stop the formation of a Schwarzschild object, an infinitely dense singularity surrounded by an event horizon. But accepting this conclusion required abandoning comfortable assumptions about how the universe worked. Many brilliant scientists simply refused to believe it could happen. Albert Einstein himself remained deeply skeptical. In 1939, he published a paper arguing that such complete collapse could never occur in nature. He suggested the equations might be mathematically correct but physically irrelevant, similar to how mathematical equations might predict impossible situations that simply never happen in the real world. Einstein believed that something would always prevent a star from shrinking beyond a certain point. Other stars might pull it apart. Rotation might create centrifugal forces that stop collapse. Quantum effects might create new pressures at extremely small scales. Surely the universe had safeguards against such absurd extremes. But in that same year, 1939, two American physicists named J. Ray Oppenheimer and Hartland Snyder published a paper that changed everything. They carefully worked through the mathematics of a collapsing massive star according to general relativity, without assuming anything except the theory itself. Their calculations showed definitively that if a star's core exceeded about 3 times the Sun's mass and nothing removed that excess mass, then no known force could prevent complete collapse to a singularity. No pressure, no quantum effect, no rotation, nothing could stop it. The star would collapse through its Schwarzschild radius and continue collapsing forever, crushed to infinite density at a single point. Oppenheimer and Snyder described how this would look to different observers. Someone falling with the collapsing star would cross the event horizon in finite time according to their own clock, experiencing nothing unusual at that boundary. They would continue falling toward the singularity, where they would be torn apart by tidal forces and crushed to infinite density. But someone watching from a safe distance would see something different. They would see the surface of the star slow down as it approached the Schwarzschild radius. Time dilation would become extreme. The star's surface would appear to freeze just above the event horizon, its light becoming increasingly redshifted until it faded into invisibility. The star would simply disappear, leaving behind an invisible gravitational trap. This paper should have settled the debate, but it did not. Many physicists still could not accept such bizarre conclusions. The idea seemed too strange, too much like science fiction. Moreover, Oppenheimer himself soon became distracted by other matters. When World War II began, he was recruited to lead the Manhattan Project, developing the atomic bomb. After the war, he became embroiled in political controversies during the Cold War. He never returned seriously to the question of stellar collapse. The problem languished, studied by only a few dedicated researchers, while most physicists focused on other areas of science. Part of the resistance came from philosophical discomfort. A singularity where density and curvature become infinite seemed to represent a breakdown of physics itself. General relativity predicted its own failure, pointing to a region where its equations no longer made sense. This bothered scientists deeply. Theories should describe nature, but here was a situation where the theory seemed to describe something physically impossible, where quantities became infinite and mathematics broke down. Perhaps this indicated that general relativity itself was incomplete, needing modification or replacement when dealing with such extreme conditions. Another source of skepticism was the sheer lack of evidence. By the 1950s, astronomers had cataloged millions of stars but had never observed anything resembling a collapsed object surrounded by an event horizon. White dwarfs had been observed. Neutron stars were suspected but not yet confirmed. But nothing suggested the existence of completely collapsed objects from which light could not escape. Without observational evidence, many scientists dismissed the idea as theoretical speculation irrelevant to the actual universe. Yet a few scientists continued thinking seriously about these objects. British physicist Roger Penrose developed sophisticated mathematical tools for studying singularities and showed that they were not just artifacts of special symmetries or simplifying assumptions. Even in realistic situations with rotation and irregularities, singularities would form. Stephen Hawking, working with Penrose, extended these results and proved that singularities were generic predictions of general relativity whenever enough mass collapsed into a small enough region. The formation of singularities was not some edge case that could be avoided. It was an inevitable consequence of Einstein's theory. By the 1960s, the tide began turning. Powerful new telescopes and instruments were discovering strange objects in the sky that seemed to require extreme physics to explain. Radio astronomers found sources of intense radio waves with no visible counterparts. X-ray astronomers detected powerful X-ray sources that flickered and varied dramatically. Theorists showed that matter falling into a collapsed object would heat up enormously, radiating vast amounts of energy before crossing the event horizon. Perhaps these mysterious sources were the observational evidence everyone had been waiting for. Perhaps nature did create these impossible objects after all. But before astronomers could find black holes, they needed a name for what they were searching for. That name would come from an unexpected source and would capture the public imagination like few scientific terms ever have. For decades, scientists struggled with what to call these theoretical objects predicted by general relativity. They used awkward phrases like collapsed stars, frozen stars, Schwarzschild singularities, or simply dark objects. Each term captured some aspect of what these things were, but none felt quite right. Collapsed stars suggested the process of formation, but not the final state. Frozen stars described what they looked like to distant observers, but someone falling in would experience anything but freezing. Schwarzschild singularities was technically accurate but cumbersome and jargon-filled. The objects needed a name that was short, memorable, and evocative, a name that captured their essential weirdness while being easy to say and remember. The term black hole first appeared in print in the late 1950s in articles by science journalist Anne Ewing, but the name did not immediately catch on. Scientists continued using their various technical terms, perhaps feeling black hole sounded too informal, too much like science fiction. The phrase remained obscure until December 1967, when physicist John Wheeler used it during a lecture at a conference in New York. Wheeler was one of the leading experts on general relativity, a brilliant scientist with a gift for memorable phrases. He had helped train many younger physicists and had an intuitive grasp of how to make complex ideas accessible. During his talk, Wheeler needed to repeatedly refer to these completely collapsed objects. Saying collapsed gravitational object or Schwarzschild singularity over and over became tedious. According to some accounts, someone in the audience suggested the term black hole during a break, though other accounts suggest Wheeler thought of it himself or heard it from a student. Regardless of the precise origin, Wheeler used the phrase in his lecture and immediately recognized its power. These objects were black because no light could escape. They were holes in space-time, regions from which nothing could return. The name was simple, dramatic, and perfect. After Wheeler's lecture, the term spread rapidly through the physics community. Some older scientists initially resisted, feeling the name was too informal or somehow undignified. British scientist Fred Hoyle briefly tried to promote the alternative term frozen star, arguing it was more technically accurate from the perspective of distant observers. But black hole had captured something essential and memorable. The name appeared in more and more papers. Science journalists loved it and used it in articles for general audiences. Within a few years, black hole had become the standard term, appearing in textbooks and technical papers alike. The name also helped change how scientists thought about these objects. A collapsed star sounded like something that had finished collapsing and stopped. A black hole sounded active and ongoing, a place where things continued falling inward forever. The name emphasized the event horizon as a boundary, a hole in space through which things could fall but never return. It highlighted the essential mystery and strangeness of these objects. They were not just very dense stars. They were fundamentally different, a new category of object requiring new ways of thinking. The term reached popular culture quickly. Science fiction writers seized on black holes as dramatic plot devices. A 1979 Disney movie called The Black Hole imagined a spaceship encountering one of these objects at the edge of space. The movie was not particularly accurate scientifically, but it brought the concept to millions of viewers. The phrase entered everyday language, used metaphorically to describe anything that swallowed things without returning them, from budget shortfalls to missing socks. This cultural penetration helped generate public interest in actual scientific research on black holes. Wheeler's gift for naming extended beyond black holes. He coined or popularized several other important physics terms, including quantum foam to describe spacetime at the smallest scales and wormhole for hypothetical tunnels through spacetime. But black hole remains his most famous legacy, a two-word phrase that perfectly captures one of nature's strangest creations. The name arrived at exactly the right moment. By the late 1960s, observational evidence was mounting that these objects really existed. Astronomers needed a name for what they were finding, and black hole served perfectly. The name helped transform black holes from obscure theoretical curiosities into objects of intense scientific study and public fascination. With a name that captured the imagination, scientists could now focus on the much harder task of actually finding these invisible objects lurking in the darkness of space. While theorists debated mathematics and philosophers worried about singularities, observational astronomers were making discoveries that would eventually prove black holes existed. These astronomers did not set out specifically to find black holes. Instead, they were exploring the universe with new types of telescopes that could detect radiation human eyes cannot see, and they kept finding mysterious objects that defied easy explanation. Radio astronomy emerged after World War II, using technologies developed for radar to detect radio waves from space. Astronomers discovered that the universe broadcasts across many wavelengths, not just the visible light our eyes can see. They found sources of intense radio emission coming from locations with no bright visible stars. Some sources were distant galaxies with active cores. Others were clouds of gas heated by the deaths of stars. But some remained mysterious, point sources of radio waves that flickered and varied in ways that seemed to require something extremely compact and energetic. In the 1960s, X-ray astronomy began revealing an even stranger universe. The Earth's atmosphere blocks X-rays from space, so detecting them required placing instruments on rockets or satellites above the atmosphere. Early X-ray missions discovered that the universe glows with high-energy radiation. The sun produces X-rays, but it is relatively dim in X-rays compared to its visible light. But scattered across the sky were sources that blazed brilliantly in X-rays while being invisible or faint in normal light. These sources required temperatures of millions of degrees, far hotter than any normal star's surface. One X-ray source discovered in 1964 particularly puzzled astronomers. Located in the constellation Cygnus, this source flickered rapidly, changing brightness over fractions of a second. The rapid variations meant the source must be very small, because light travel time limits how quickly an object can change. Something the size of the sun cannot flicker in less than a second, because light takes more than a second to cross it. The Cygnus X1 source, as it was named, had to be smaller than the Earth yet produced more X-ray energy than 1,000 suns. What could possibly generate such power from such a small volume? Astronomers turned optical telescopes toward Cygnus X1's position and found a massive blue supergiant star called HD 226868. This star seemed normal except that it wobbled back and forth regularly, pulled by the gravity of an invisible companion. By measuring the wobble, astronomers could calculate that the invisible companion contained at least 6 times the sun's mass. An invisible object that massive should be visible. Normal stars that heavy shine brilliantly. Even white dwarfs and neutron stars at that mass would be detectable. Yet nothing could be seen. The companion was dark and compact, and somehow it generated enormous amounts of X-ray radiation. The explanation gradually became clear. Matter from the blue supergiant was being pulled away by the intense gravity of its dark companion, forming a swirling disk of gas around the invisible object. As the gas spiraled inward, friction heated it to millions of degrees, hot enough to glow brightly in X-rays. Just before crossing the event horizon, matter would release a final burst of radiation before disappearing forever. The system was acting like a cosmic furnace, converting gravitational potential energy into light with incredible efficiency. But only a black hole could be so massive yet so compact, with no surface to emit light of its own. Throughout the 1970s, astronomers found more X-ray binary systems where visible stars orbited invisible companions. Each time they measured the invisible object's mass and found it exceeded 3 solar masses, the limit beyond which neutron stars cannot exist. These systems showed flickering and rapid variations that required extremely compact sources. Some showed jets of material shooting outward at nearly the speed of light. The evidence mounted that these invisible companions were black holes, the first examples of these theoretical objects actually found in nature. But astronomers remained cautious. Measuring masses in binary star systems involves uncertainties. Perhaps the invisible objects were neutron stars that somehow appeared more massive than they really were. Perhaps some unknown type of object existed that theory had not predicted. The evidence was suggestive, but not definitive. What astronomers really needed was to find black holes in other contexts where their presence would be undeniable. That evidence would come from an unexpected direction, from the centers of galaxies where something far more massive and powerful than stellar black holes was lurking. The X-ray sources like Cygnus X1 represented stellar mass black holes, formed from the deaths of massive. They typically contained between 3 and 20 times the sun's mass. But nature also created black holes on a completely different scale, millions or even billions of times more massive than the sun. These supermassive black holes would provide some of the most dramatic and convincing evidence that black holes really existed. And they would reveal that black holes were not just exotic curiosities lurking in dark corners of the galaxy. Instead, they sat at the very centers of galaxies, controlling the motions of billions of stars and shaping the evolution of cosmic structure itself. The story of how astronomers discovered supermassive black holes and unraveled their role in the cosmos, represents one of the great detective stories in the history of science. In the early 1960s, astronomers made a discovery that seemed impossible at first. Using radio telescopes, they detected objects that looked like stars through optical telescopes but emitted radio waves with incredible intensity. When they measured the spectra of these objects, the wavelengths of light were shifted so far toward the red end of the spectrum that it took time to realize what they were seeing. These objects sat billions of light-years away, farther than any objects previously observed. Yet despite their enormous distances, they shone as brightly as hundreds of entire galaxies, each containing hundreds of billions of stars. Something out there was generating more power than we could easily explain, concentrated in regions smaller than our solar system. Astronomers called these objects quasars, short for quasi-stellar radio sources. Their discovery sparked intense debate about what could possibly generate such power. Some scientists initially questioned whether they really were as distant as their redshifts indicated. Perhaps these were nearby objects with unusual properties that only made them look distant. But as more quasars were found and studied, their cosmological distances became undeniable. They really were billions of light-years away, shining with the light of trillions of suns. The universe contained objects far more powerful than anyone had imagined. The puzzle deepened when astronomers noticed that quasars varied in brightness over days. This meant their energy source occupied a region only light days or light weeks across, smaller than our solar system. Imagine compressing the energy output of an entire galaxy into a space that would fit comfortably between the sun and the outer planets. What mechanism could possibly achieve this? Nuclear fusion, the process that powers stars, could not produce enough energy in such a small space. Chemical reactions were far too weak. Matter-antimatter annihilation could produce sufficient energy, but where would you get that much antimatter? The problem seemed impossible. British astronomer Donald Lynden Bell and others proposed a radical solution in the late 1960s. What if quasars were powered by supermassive black holes, objects containing millions or billions of times the sun's mass, sitting at the centers of distant galaxies? Matter falling into such a black hole would form an accretion disk, similar to the disks around stellar mass black holes but vastly larger and more powerful. The intense gravity would heat the disk to millions of degrees, making it glow brilliantly across all wavelengths. Strong magnetic fields could channel some of the infalling matter into jets shooting outward at near light speed. Such a system could explain both the incredible luminosity of quasars and their compact size. This hypothesis seemed wild at first. Where would supermassive black holes come from? How would they form? Why would they sit at galaxy centers? But as astronomers studied more quasars and similar objects called active galactic nuclei, the supermassive black hole explanation became increasingly compelling. The physics worked. The energetics made sense. Alternative theories struggled to explain the observations. Most importantly, if supermassive black holes powered quasars, then similar objects should exist in nearby galaxies, perhaps sitting quietly because they were not currently consuming large amounts of matter. Astronomers began looking carefully at the centers of nearby galaxies, measuring how stars and gas moved in those central regions. They found something remarkable. In galaxy after galaxy, objects near the center orbited at extremely high speeds, far faster than expected based on the visible matter. Something massive and invisible sat at the very center, controlling the motions of everything around it. In our own Milky Way galaxy, astronomers tracked stars orbiting the galactic center and found they were moving at thousands of kilometers per second. Only a black hole containing millions of solar masses could explain such rapid motion in such a small region. The best studied case became the center of the giant elliptical galaxy, Messier 87, located about 50 million years away in the Virgo cluster. This galaxy showed a bright jet of material shooting thousands of light-years from its core. Observations with the Hubble Space Telescope in the 1990s revealed gas orbiting the center at incredibly high speeds, implying the presence of a black hole containing more than 6 billion times Sun's mass. Similar measurements in other galaxies kept finding the same pattern. The biggest galaxies contained the biggest central black holes. A relationship existed between the mass of the black hole and properties of the surrounding galaxy, suggesting that black holes and galaxies evolved together. These discoveries fundamentally changed our understanding of cosmic structure. Black holes were not rare oddities. Every large galaxy appeared to contain a supermassive black hole at its center. Our Milky Way hosts a black hole named Sagittarius A star, containing about 4 million solar masses, sitting 26,000 light-years away at the galaxy's center. These black holes play crucial roles in galaxy evolution. When they consume matter actively, they shine as quasars or active galactic nuclei, pumping enormous energy into their surroundings. This energy can heat gas throughout the galaxy, preventing it from cooling and forming new stars. The black holes at galaxy centers act like thermostats, regulating star formation and shaping how galaxies grow and change over billions of years. The existence of supermassive black holes raised new questions. How did they form? Did they grow from stellar mass black holes that merged and consumed matter over billions of years? Or did they form differently, perhaps directly from the collapse of enormous gas clouds in the early universe? Why do they correlate with galaxy properties? What determines the relationship between black hole mass and galaxy characteristics? These questions drove decades of research and continue to fascinate astronomers today. But by the 1990s, the existence of black holes, both stellar mass and supermassive, had become accepted fact rather than speculative theory. The next frontier became studying their detailed properties and searching for more direct evidence of event horizons and the strange physics predicted near them. While observational astronomers searched the skies for black holes, theoretical physicists worked to understand their detailed properties and implications. No scientist contributed more to this understanding than Stephen Hawking, whose name became synonymous with black holes for both scientists and the general public. Hawking's journey and discoveries illuminate both the strange physics of black holes and the human drama of scientific discovery. Born in Oxford, England in 1942, exactly 300 years after Galileo's death, as he liked to note, Hawking showed early interest in how things worked. He studied physics at Oxford University and then moved to Cambridge for graduate work in cosmology. At age 21, during his first year at Cambridge, he began experiencing problems with balance and slurred speech. Doctors diagnosed him with amyotrophic lateral sclerosis, a disease that progressively destroys nerve cells controlling muscles. They gave him 2 years to live. Against all odds, Hawking survived. The disease progressed more slowly than predicted, though it gradually paralyzed him completely. He learned to work differently, developing extraordinary abilities to visualize complex equations and geometric structures in his mind without writing them down. As his speech deteriorated, he eventually communicated through a computer system controlled by tiny muscle movements, speaking in a synthesized voice that became famous worldwide. His physical limitations somehow seemed to enhance his mental powers, allowing him to think about physics in uniquely intuitive ways. In his doctoral research, Hawking worked with Roger Penrose on singularity theorems. Together, they proved mathematically that singularities were not artifacts of special assumptions or perfect symmetries. Given reasonable starting conditions and Einstein's equations, singularities inevitably formed. This work established that black holes were genuine predictions of general relativity, not mathematical curiosities that could be. The universe really did contain these strange objects, and their centers really did contain singularities where physics broke down. But Hawking's most famous discovery came in 1974 when he combined general relativity with quantum mechanics, the theory describing how particles behave at the smallest scales. These two theories were notoriously difficult to merge. They seemed to operate on different principles with different mathematics. But Hawking found a way to apply quantum mechanics to the region just outside a black hole's event horizon. What he discovered shocked the physics community. According to quantum mechanics, empty space is not truly empty. Instead, it seethes with virtual particles that constantly appear and disappear in particle-antiparticle pairs, popping briefly into existence before annihilating each other. Normally, these virtual particles cannot be observed directly because they exist for such short times. But Hawking showed that near a black hole's event horizon, something remarkable could happen. A particle-antiparticle pair could appear just outside the horizon, with one particle falling into the black hole while the other escaped to infinity. To a distant observer, it would appear as if the black hole had emitted a particle. This Hawking radiation meant that black holes were not completely black. They glowed faintly with thermal radiation, like warm objects radiating heat. The temperature was incredibly low, much colder than the cosmic microwave background radiation filling all of space, so no existing black hole actually glowed brightly. But the principle was revolutionary. Black holes had a temperature. They radiated energy. And since they radiated energy, they were losing mass, slowly evaporating. Given enough time, far longer than the current age of the universe, black holes would completely evaporate away, ending their existence not with infinite permanence, but with a final burst of radiation. This discovery created paradoxes that still puzzle physicists today. If black holes eventually evaporate completely, what happens to the information about everything that fell in? Quantum mechanics says information cannot be destroyed, but if the black hole evaporates into random radiation, the information seems lost. This information paradox has driven decades of theoretical research, leading to insights about quantum gravity, string theory, and the fundamental nature of space-time itself. Hawking spent much of his later career working on this problem, eventually proposing that information somehow escapes encoded in the Hawking radiation. Hawking also made important contributions to understanding black hole thermodynamics. In collaboration with other physicists, particularly Jacob Bekenstein, he showed that black holes obey laws remarkably similar to the laws of thermodynamics that govern heat and energy in ordinary systems. Black holes have entropy proportional to the area of their event horizons. They have temperature related to their surface gravity. These connections between gravity, quantum mechanics, thermodynamics suggest deep relationships between different areas of physics, hints that a more fundamental theory might unify them all. Beyond his scientific contributions, Hawking became one of the most recognizable scientists in the world. His book A Brief History of Time, published in 1988, became an international bestseller, introducing millions of readers to cosmology and black holes. He appeared on television shows, in documentaries, and even in science fiction programs. His synthesized voice became iconic. His courage in continuing to work despite devastating disability inspired people worldwide. He showed that the human mind could overcome physical limitations, that pure thought could probe the deepest mysteries of reality. Hawking died in March 2018, having far outlived his initial diagnosis by more than 5 decades. His funeral at Cambridge was attended by colleagues and admirers from around the world, while his ashes were interred in Westminster Abbey, between the graves of Isaac Newton and Charles Darwin, an honor reserved for Britain's greatest scientists. His legacy extends beyond specific discoveries to include inspiring new generations of physicists and showing the public that science could be exciting, accessible, profoundly meaningful. The physics of black holes bears his stamp permanently. From Hawking radiation to the resolution of singularity problems to the profound connections between black holes and quantum mechanics that continue to drive theoretical research today, black holes present a unique challenge to astronomy. They are invisible by definition, emitting no light of their own. So how can astronomers find and study them? The answer lies in detecting their effects on surrounding matter and space. Black holes may be invisible, but they leave unmistakable fingerprints through their intense gravity and the behavior of material falling toward them. The primary method for detecting stellar mass black holes involves binary star systems, where a visible star orbits an invisible companion. By carefully observing the visible star's motion, astronomers can determine the orbit's shape and period. Using Newton's laws of motion and gravity, they can then calculate the invisible companion's mass. If that mass exceeds about 3 times the Sun's mass, the object cannot be a neutron star or white dwarf. It must be a black hole or something even more exotic. By the early 2000s, astronomers had identified dozens of these systems, building statistical confidence that stellar mass black holes were common in our galaxy. The material falling toward a black hole from a companion star creates spectacular displays. As gas from the normal star is pulled toward the black hole, it forms an accretion disk, a flat spiral of material orbiting the black hole at increasing speeds as it falls inward. Friction within the disk generates intense heat, raising temperatures to millions of degrees. The disk glows brilliantly in X-rays and other high-energy radiation. Just before crossing the event horizon, matter releases a final surge of energy, making the innermost regions of accretion disks among the brightest objects in the universe for their size. These accretion disks are not steady. They flicker and vary on timescales from milliseconds to months, creating light curves that astronomers can analyze for information about the black hole. Rapid variations indicate small sources, constraining the black hole's size. The spectrum of radiation reveals the temperature and density of material in different parts of the disk. Sometimes a blob of hot gas orbits very close to the event horizon, creating a periodic signal as it whips around multiple times per second before finally falling in. These quasi-periodic oscillations provide information about conditions in the strongest gravitational fields in the universe. For supermassive black holes at galaxy centers, detection methods are different, but based on the same principle of observing gravity's effects. Astronomers measure the velocities of stars or gas clouds orbiting the galactic center. Stars near the center of our Milky Way have been tracked for decades as they orbit the invisible mass at Sagittarius A star. These stars move at incredible speeds, some completing orbits in just a few years, despite being billions of kilometers from the black hole. One star designated S2 approached within 17 light hours of the black hole in 2018, reaching speeds of nearly 5,000 kilometers per second. Tracking its orbit allowed precise measurement of the black hole's mass, at about 4.1 million solar masses. Similar measurements in other galaxies require more indirect methods because individual stars are too faint to see at such distances. Instead, astronomers measure the overall motion of stars or gas in the galaxy's central region using spectroscopy. The Doppler shift of light reveals how fast material is moving toward or away from Earth. By mapping these velocities at different positions, astronomers can determine how much mass sits at the galaxy's center and how compact it is. Time and again, these measurements reveal enormous masses in tiny volumes, masses that can only be black holes. Radio astronomy provides another powerful tool for studying black holes, particularly supermassive ones. Many active galactic nuclei produce jets of material shooting outward from near the black hole at nearly the speed of light. These jets emit radio waves strongly, creating bright radio sources that can be detected across billions of light years. The jets are powered by black hole rotation and strong magnetic fields threading through the accretion disk. Material in the inner disk gets channeled along magnetic field lines and accelerated outward to relativistic speeds. These jets can extend for millions of light years, far beyond the host galaxy, affecting the evolution of entire galaxy clusters. Gravitational effects provide yet another detection method. Black holes bend light through gravitational lensing, a prediction of general relativity confirmed many times. When a black hole passes between Earth and a more distant star, the black hole's gravity bends the distant star's light, causing the star to brighten temporarily as we see multiple magnified images. This microlensing effect has detected isolated black holes drifting through the galaxy, objects with no companion stars and no accretion disks, completely dark but revealed through their gravitational influence. Perhaps the most dramatic development in detecting black holes came from gravitational wave astronomy. Einstein predicted that accelerating masses should create ripples in space-time itself that propagate outward at the speed of light. These gravitational waves are incredibly weak, requiring catastrophic events like colliding black holes to produce detectable signals. In 2015, the Laser Interferometer Gravitational Wave Observatory called LIGO detected gravitational waves for the first time, coming from two black holes that had spiraled together and merged more than 1 billion light-years away. The signal lasted a fraction of a second but contained extraordinary information about the black hole's masses, spins, and final merger. This detection opened an entirely new way of observing the universe, allowing astronomers to detect black holes directly through a warping of space-time rather than through their effects on matter and light. Each of these detection methods has strengths and limitations, but together they paint a consistent picture. Black holes exist throughout the universe in a range of masses. They interact with their surroundings in ways precisely predicted by general relativity. They power some of the most energetic phenomena in the cosmos, and they can be studied in increasingly sophisticated ways as technology improves. The hunt for black holes has evolved from debating their existence to cataloging their properties, understanding their roles in cosmic evolution, and using them as laboratories for testing fundamental physics under extreme conditions impossible to recreate on Earth. While stellar mass black holes form from dying stars, and typically contain between 3 and 20 times the Sun's mass. Supermassive black holes occupy an entirely different scale. These monsters contain millions or billions of times the Sun's mass, concentrated in regions not much larger than our solar system. They sit at the centers of nearly every large galaxy, including our own Milky Way. Their origin, growth, and influence on galaxy evolution represent some of the most active areas of research in modern astrophysics. The discovery that galaxies host supermassive black holes at their centers came gradually through multiple lines of evidence. Observations of quasars and active galactic nuclei in the 1960s and 70s showed that something incredibly massive and compact powered these luminous objects. Measurements of stellar and gas velocities near galaxy centers in the 1980s and 90s kept finding large, invisible masses. By the late 20th century, astronomers had established beyond reasonable doubt that supermassive black holes were common, perhaps universal, in large galaxies. But this discovery immediately raised a puzzle. Where did these supermassive black holes come from? They were too massive to form from single stars, even the largest stars ever observed. Several formation scenarios have been proposed. Perhaps they formed from the deaths of the very first generation of stars in the early universe, which might have been much more massive than modern stars. These seed black holes could then grow by consuming gas and merging with other black holes over billions of years. Alternatively, supermassive black holes might have formed directly from the collapse of enormous gas clouds in the early universe, bypassing the stellar stage entirely. Understanding how black holes grow involves understanding accretion, the process of matter falling inward. An isolated black hole in empty space will simply sit there, unchanging except for the incredibly slow evaporation through Hawking radiation. But a black hole surrounded by gas and dust will pull that material inward, growing steadily. The rate of growth depends on how much material is available and how efficiently it can fall inward. Material with angular momentum cannot fall straight in, but instead forms an accretion disk, gradually spiraling inward as friction removes energy and angular momentum. Accretion disks around supermassive black holes can be enormous, extending for light years and containing millions or billions of times the Earth's mass in gas. These disks glow brilliantly as friction heats them, making active galactic nuclei among the brightest objects in the universe. The innermost regions reach temperatures of millions of degrees, emitting X-rays and ultraviolet light. Outer regions are cooler, emitting visible and infrared light. The disk's spectrum contains information about temperature, density, and composition at different radii. But accretion disks do more than just glow. They launch powerful winds and jets that can affect entire galaxies. Strong magnetic fields threading through the disk can extract rotational energy from the black hole itself through a process called the Blandford-Znajek mechanism. These fields channel material into narrow jets shooting outward along the black hole's rotation axis at close to the speed of light. The jets carry enormous energy and momentum, capable of blowing gas out of galaxies and preventing new star formation for millions of light years around the black hole. This feedback between supermassive black holes and their host galaxies appears crucial for understanding galaxy evolution. Without black holes, galaxies would likely convert much more of their gas into stars, forming galaxies very different from what we observe. The energy from active black holes heats gas, preventing it from cooling and collapsing to form stars. This self-regulation may explain observed correlations between black hole mass and galaxy properties. The more massive the black hole, the more feedback energy it can generate, the more it can regulate star formation, leading to specific relationships between black hole mass and the mass or velocity dispersion of stars in the galactic center. Observations have revealed a remarkable correlation between supermassive black hole mass and the properties of the galaxy's central bulge. Black holes in galaxies with massive bulges are themselves more massive, following a tight relationship that holds across a wide range of galaxy types and masses. This correlation suggests that black holes and galaxies evolve together through cosmic time, each influencing the other's growth. Understanding this coevolution represents a major challenge in astrophysics, requiring sophisticated computer simulations that model both black hole physics and galaxy dynamics over billions of years. Supermassive black holes can also grow by merging with other black holes. When two galaxies collide and merge, Their central black holes eventually sink toward the center of the merged galaxy and orbit each other. Over millions of years, gravitational wave emission and interactions with stars gradually shrink the orbit until the black holes merge in a violent collision that releases enormous gravitational wave energy. These mergers create even more massive black holes and can kick the merged black hole out of the galaxy center due to asymmetric gravitational wave emission. The most extreme supermassive black holes discovered so far contain tens of billions of solar masses. These ultramassive black holes sit at the centers of the largest galaxies in the universe. How they grew so large remains uncertain. Some may have formed in special circumstances in the early universe. Others may have grown through particularly efficient accretion or through multiple mergers. Finding and studying these most extreme cases helps constrain theories of black hole formation and growth. Despite decades of research, many questions about supermassive black holes remain open. How common are intermediate mass black holes with masses between stellar and supermassive? These would help bridge the gap between different black hole populations but have proven difficult to find conclusively. What determines when a supermassive black hole is active versus quiet? Our galaxy's black hole is relatively quiet today, but was it more active in the past? How exactly do black hole jets form and maintain their coherence over millions of light years? These questions drive ongoing research using ever more powerful telescopes and instruments, seeking to understand these massive beasts that sit at the hearts of galaxies and shape cosmic evolution on the grandest scales. The event horizon represents the most important boundary in the universe. It is the point of no return, the surface of no escape, the ultimate one-way membrane. Outside the event horizon, even very close to it, escape remains theoretically possible, though incredibly difficult. Inside the event horizon, escape becomes absolutely impossible. All paths through space-time lead inward toward the singularity. Even light cannot move outward. The event horizon defines what makes a black hole black and marks the boundary beyond which we can never receive information about events occurring inside. For a non-rotating black hole, described by the Schwarzschild solution, the event horizon sits at the Schwarzschild radius, a distance proportional to the black hole's mass. For a black hole with the sun's mass, this radius would be about 3 kilometers. For a black hole with 1,000,000 solar masses, it would be about 3 million kilometers, roughly twice the sun's actual radius. For the 4 million solar mass black hole at our galaxy's center, the event horizon has a radius of about 12 million kilometers, small enough to fit comfortably inside the orbit of Mercury, but large enough to swallow planets whole. What happens to someone or something falling through an event horizon? The answer depends on perspective. From the viewpoint of someone far away watching the fall, something strange occurs. As the falling object approaches the event horizon, time dilation becomes extreme. Clocks on the falling object appear to tick slower and slower. Light from the object becomes increasingly redshifted, stretched to longer wavelengths. The object appears to slow down, approaching the horizon more and more gradually, freezing asymptotically at the boundary. The object's image fades and reddens until it disappears into invisibility. From the outside perspective, the object never quite crosses the horizon, it appearing to freeze at the boundary forever. But from the perspective of someone falling into the black hole, the experience is completely different. They feel nothing special at the moment they cross the event horizon. There is no barrier, no wall, no sudden change. If the black hole is large enough, tidal forces at the horizon might be gentle enough that the falling observer notices nothing unusual at all. They cross the boundary and continue falling inward, local clocks ticking normally, light behaving normally from their perspective. The weirdness of the event horizon is not locally dramatic. It only becomes apparent when trying to communicate with the outside universe. Once inside the event horizon, the geometry of space-time changes fundamentally. Outside the horizon, moving outward is possible even if difficult. Inside the horizon, the inward direction toward the singularity becomes as inevitable as moving forward in time. Just as you cannot prevent time from advancing into the future, you cannot prevent falling toward the singularity once inside the event horizon. All possible paths through space-time, even those where you accelerate as hard as possible in any direction, lead to the singularity in a finite amount of proper time. The time to reach the singularity after crossing the event horizon depends on the black hole's mass. For a stellar mass black hole, it would be microseconds. For a supermassive black hole, it could be hours or even days. But that the journey's end is certain. As you fall, tidal forces grow stronger. These forces arise because gravity is slightly stronger on parts of your body closer to the singularity than parts farther away. Near a stellar mass black hole, tidal forces become lethal long before crossing the event horizon, stretching you like taffy in what physicists playfully call spaghettification. Near a supermassive black hole, the tidal forces at the horizon might be survivable, allowing a journey some distance inside before they become deadly. Eventually, as you approach the singularity, tidal forces grow infinite. The stretching in one direction and compression in perpendicular directions becomes unbearable, then lethal, then so extreme that atoms themselves are torn apart. All matter is crushed to infinite density at a single point or ring, depending on whether the black hole rotates. The laws of physics as we understand them break down. General relativity predicts its own failure, pointing to a regime where quantum effects of gravity become important, but where we have no complete theory to describe what happens. What really exists at the singularity? Does infinite density actually occur, or does some quantum effect prevent it? Does the singularity connect to other regions of space-time, perhaps even other universes through wormholes? These questions touch the frontiers of theoretical physics. Many physicists suspect that quantum gravity effects, described by a complete theory we do not yet possess, would prevent true infinities from occurring. Perhaps the singularity is replaced by a region of extremely high but finite density and curvature. Perhaps string theory or loop quantum gravity provides a more complete description. These questions remain open, driving research in theoretical physics. Rotating black holes, described by the Kerr solution discovered in 1963, have even stranger properties. They possess not one but two event horizons, an outer one and an inner one, with a region between called the ergosphere, where space-time itself is dragged around by the black hole's rotation. In the ergosphere, it becomes impossible to remain stationary relative to distant stars. You are forced to rotate with the black hole even if you fire rockets trying to resist. The ergosphere allows a process called the Penrose process, where energy can be extracted from a rotating black hole, potentially allowing advanced civilizations to use black holes as power sources. Inside the inner event horizon of a rotating black hole, the geometry becomes even more bizarre. Some mathematical solutions suggest the singularity might form a ring rather than a point, and that it might be possible to pass through the ring into other regions of space-time. These solutions inspire speculation about wormholes and time travel, though most physicists believe quantum effects or instabilities would prevent such exotic structures from actually existing. The interior of black holes remains the most mysterious region in the known universe, a place where our theories point toward fascinating possibilities while admitting their own incompleteness. Perhaps nothing about black holes captures the imagination more than their effect on time itself. According to general relativity, gravity does not just pull objects together. It warps the very fabric of space-time, affecting how time flows and how distances measure. Near a black hole, these effects become extreme, leading to phenomena that seem impossible yet are thoroughly predicted by Einstein's equations, and in weaker forms, have been measured experimentally. Time dilation, the slowing of time in gravitational fields, occurs everywhere gravity exists, but becomes dramatic near black holes. A clock sitting on Earth's surface runs slightly slower than a clock in orbit, losing about 1 microsecond per century compared to a clock far from any gravitational field. This effect is small but real and must be accounted for in GPS satellite systems. Without correcting for gravitational time dilation, GPS positions would drift by kilometers per day. The effect's been measured directly in laboratories by comparing atomic clocks at different altitudes, confirming Einstein's predictions with remarkable precision. Near a black hole, time dilation becomes far more extreme. At a distance of twice the Schwarzschild radius, a clock runs about 30% slower than a clock far from the black hole. At the event horizon itself, time dilation becomes infinite from the perspective of a distant observer. A clock at the horizon would appear completely frozen to someone far away, ticking infinitely slowly, taking forever to advance even 1 second. This is why distant observers see objects approaching the event horizon appear to freeze. The light reaching the outside observer shows time running slower and slower for the falling object until time appears to stop completely at the horizon. But for someone falling into the black hole, their own clock ticks normally. They do not experience time slowing down. Instead, they see time in the outside universe speeding up. Looking back at the universe they left behind, they would see events occurring faster and faster. Stars would age rapidly. Civilizations would rise and fall in moments. If they fell through the event horizon of a supermassive black hole and looked back, they might see the entire future history of the universe flash before their eyes in the final moments before reaching the singularity. This difference in time flow creates paradoxes that have puzzled physicists for decades. If time stops at the event horizon from an outside perspective, how can we say black holes form at all? From the outside, collapsing stars appear to freeze just above their Schwarzschild radii, never quite forming complete black holes. Yet from the perspective of the collapsing matter, the collapse completes in finite time, forming a singularity. Both perspectives are equally valid within general relativity, describing the same physics from different viewpoints. There is no absolute universal time that would resolve the apparent contradiction. The combination of time dilation and frame dragging near rotating black holes creates regions where closed time-like curves might exist, paths through space-time that loop back on themselves. Following such a path would allow traveling backward in time, meeting your own past self, creating all the paradoxes that time travel stories explore. Do these curves really exist near black holes, or do quantum effects or instabilities prevent them? This remains an open question in theoretical physics, touching deep issues about the nature of causality and the relationship between general relativity and quantum mechanics. Black holes also affect time through gravitational waves. When black holes merge, they create ripples in space-time that propagate outward at the speed of light. These gravitational waves carry energy away from the system, causing the orbits to decay and the black holes to spiral together. The final moments of a black hole merger produce gravitational waves of incredible intensity, warping space-time by measurable amounts even after traveling billions of light years. LIGO and other gravitational wave detectors measure these distortions by using laser interferometry to detect changes in distance of less than the width of an atomic nucleus. The gravitational wave signal from merging black holes contains extraordinary information encoded in how the signal's frequency and amplitude change over time. The inspiral phase, when the black holes circle each other at increasing speeds, reveals their masses and distance. The merger phase, when they collide and combine, tests Einstein's equations in the strongest gravitational fields that exist. The ring-down phase, when the merged black hole settles into a stable configuration, reveals the final black hole's mass and spin. Every detected merger provides both confirmation of general relativity and tests of possible deviations from Einstein's theory. Some physicists speculate that quantum effects might create firewalls at event horizons, surfaces of incredibly high energy that would destroy anything trying to cross. This proposal attempts to resolve the black hole information paradox by ensuring that information never truly enters the black hole interior. Other physicists argue that firewalls would violate principles of general relativity and that the information paradox must be resolved differently. These debates touch fundamental questions about quantum mechanics and gravity work together, questions that a complete theory of quantum gravity would answer. Time's behavior near black holes represents both a triumph of Einstein's theory and a window into physics beyond what we currently understand. The predictions of general relativity about time dilation and gravitational waves have been confirmed repeatedly by observation. Yet the ultimate behavior of time at singularities and the reconciliation of time's nature between quantum mechanics and general relativity remain open problems. Black holes force us to confront the strangeness of time itself, revealing that this most familiar aspect of our experience is far more flexible and mysterious than everyday intuition suggests. For a century after Einstein predicted them, gravitational waves remained theoretical curiosities, ripples in space-time that were extremely difficult to detect. The challenge was immense. Gravitational waves are incredibly weak by the time they reach Earth, even from the most violent events in the universe. Detecting them requires measuring changes in distance far smaller than an atomic nucleus over kilometers of separation. Many physicists doubted whether detection would ever be possible. But beginning in the late 20th century, scientists began building instruments capable of this seemingly impossible measurement. The concept is elegant in principle. A gravitational wave passing through space alternately stretches and squeezes distances in perpendicular directions. If you could precisely measure the distance between widely separated masses, a passing gravitational wave would cause measurable oscillations. The challenge is making measurements precise enough to detect distortions of less than 1 part in 10 to the 21st. This would be like measuring the distance to the nearest star to an accuracy smaller than the width of a human hair. Laser interferometry provides the necessary precision. The Laser Interferometer Gravitational Wave Observatory, called LIGO, consists of 2 facilities in Washington State and Louisiana, each with 2 perpendicular arms 4 kilometers long. Laser light bounces back and forth between mirrors at the ends of the arms, and detectors compare the light's phase from the 2 arms. When a gravitational wave passes through, one arm stretches while the other compresses, creating a measurable difference in the light's travel time. The 2 widely separated facilities allow distinguishing real gravitational wave signals from local noise and help determine the source's direction in the sky. Building and operating LIGO required technological breakthroughs in lasers, optics, vibration isolation, and data analysis. The mirrors must be isolated from seismic vibrations, passing trucks, ocean waves, and countless other disturbances. The laser light must be incredibly stable and intense. The data analysis must distinguish real signals from noise events that can mimic gravitational waves. Thousands of scientists and engineers worked on the project for decades before it became sensitive enough to detect anything. On September 14, 2015, LIGO detected its first gravitational wave signal. The event appeared nearly simultaneously at both facilities, a chirp lasting only a fraction of a second. The signal showed the characteristic pattern of 2 massive objects spiraling together and merging, their orbital frequency increasing as they accelerated toward collision. Analysis revealed that 2 black holes, one containing about 36 solar masses and the other about 29 solar masses, had merged about 1.3 billion years ago. The collision released energy equivalent to 3 solar masses, converted entirely into gravitational waves according to Einstein's famous equation E equals mc squared. This single event radiated more power in gravitational waves than all the stars in the observable universe combined were radiating in light at that moment. The detection announcement in February 2016 electrified the scientific community and captured worldwide attention. It confirmed a century-old prediction of general relativity. It demonstrated that gravitational wave astronomy was possible. And it provided the first direct evidence that binary black holes existed and could merge, something that had been predicted but never directly observed. The discovery was honored with the 2017 Nobel Prize in Physics awarded to Rainer Weiss, Barry Barish, and Kip Thorne for their leadership in making LIGO successful. Since that first detection, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, mostly from merging black holes but also from colliding neutron stars. Each detection reveals new information about the population of compact objects in the universe. The black holes detected through gravitational waves often have higher masses than those found through X-ray astronomy, suggesting there may be multiple populations formed through different processes. Some mergers involve black holes with very different masses. Others involve nearly equal masses. The distribution of spins and masses provides clues about how black holes form and evolve. One particularly remarkable detection in August 2017 came from 2 neutron stars merging rather than black holes. This event was different because neutron stars, unlike black holes, have surfaces that emit light. The gravitational wave detection triggered a massive observing campaign involving telescopes across the electromagnetic spectrum. Within seconds of the LIGO and Virgo detection, gamma-ray satellites detected a short burst from the same direction. Hours later, optical telescopes found a new bright object in a galaxy 130 million light-years away. Follow-up observations showed the characteristic signatures of a kilonova, an explosion powered by radioactive decay of heavy elements formed in neutron star mergers. This multi-messenger observation confirmed that neutron star mergers create heavy elements like gold and platinum, solving a decades-old mystery about where these elements come from. Gravitational wave detections also test Einstein's general theory of relativity in its most extreme regime. The waves come from regions of such intense gravity that space-time is stretched and compressed by measurable amounts. The signals probe what happens when black holes move at significant fractions of light speed, when gravitational fields are billions of times stronger than anywhere in our solar system. So far, every detection matches the predictions of general relativity beautifully. No deviations have been found despite careful searching. This provides confidence that Einstein's theory correctly describes gravity even in the most extreme environments we can observe. Future gravitational wave detectors promise even more exciting discoveries. The European Space Agency plans to launch LISA, the Laser Interferometer Space Antenna, in the 2030s. LISA will consist of 3 spacecraft in solar orbit, separated by millions of kilometers, forming a giant triangular detector in space. It will be sensitive to lower-frequency gravitational waves than ground-based detectors, allowing it to detect supermassive black holes merging in the distant universe. It might detect thousands of such mergers, mapping the growth of black holes and galaxies throughout cosmic history. Ground-based detectors are being upgraded to higher sensitivity, and new facilities are being built in Japan and India. These improvements will increase the detection rate from dozens per year to potentially hundreds per year, building statistical samples large enough to study black hole populations in detail. As gravitational wave astronomy matures, it transforms from making individual remarkable discoveries to becoming a routine tool for studying the universe, complementing traditional astronomy with an entirely new way of observing cosmic events. The era of gravitational wave astronomy marks a fundamental shift in how we study the universe. For thousands of years, astronomy relied on light in various forms, from visible light to radio waves to gamma rays. Now we can observe with gravitational waves ripples in space-time itself. This allows studying events and objects that produce little or no light, like black hole mergers. Provides independent measurements of cosmic distances and expansion rates. And it offers a way to test fundamental physics in regimes impossible to access any other way. Gravitational wave astronomy represents one of the great achievements of 21st century science, opening windows onto the universe that previous generations could only imagine. One of the most stunning achievements in black hole astronomy came in April 2019 when scientists unveiled the first image of a black hole's shadow. This photograph represented decades of work, incredible technological achievement, and international cooperation. It showed a glowing ring surrounding a dark circular region, the shadow of the event horizon itself, direct visual evidence that matched theoretical predictions with remarkable accuracy. The target was the supermassive black hole at the center of Messier 87, a giant elliptical galaxy about 55 million light-years away. This black hole contains about 6.5 billion solar masses and sits at the center of a bright jet visible across millions of light-years. Despite its enormous mass, the black hole's event horizon has an angular size as viewed from Earth of only about 40 microarcseconds, equivalent to seeing a tennis ball on the moon. No single telescope on Earth could possibly resolve such a tiny angle. The image required combining data from radio telescopes scattered across the entire planet, creating an Earth-sized virtual telescope. The technique is called very long baseline interferometry. Multiple radio telescopes observe the same object simultaneously, recording the radio waves they detect along with precise timing information from atomic clocks. Later, the data streams are combined by computer, comparing the signal's phase and timing to reconstruct an image with resolution equivalent to a telescope as large as the separation between the facilities. For the Event Horizon Telescope project, 8 radio telescope facilities on 4 continents participated, from Spain to Chile to Antarctica to Hawaii, creating baselines as long as Earth's diameter. Collecting the data required exquisite planning and coordination. All telescopes had to observe simultaneously, pointed at the same target during brief windows when weather and technical conditions were favorable at all sites. The radio observations happened at a wavelength of 1.3 millimeters, chosen because it penetrates the gas and dust surrounding the black hole, while also being short enough to provide high resolution. Each telescope recorded petabytes of data, far too much to transmit over the internet. Instead, the data was stored on hard drives and physically shipped to central processing facilities where specialized supercomputers correlated the signals. Processing the data took months of intensive computation. The raw data from different telescopes had to be precisely synchronized and combined, accounting for Earth's rotation, atmospheric delays, and instrumental effects. The radio waves from the black hole's vicinity are scrambled by ionized gas in the Milky Way and in Messier 87 itself, requiring careful modeling to remove these distortions. Multiple analysis teams worked independently using different algorithms and approaches, comparing results to ensure the final image reflected real structure rather than processing artifacts. On April 10, 2019, the Event Horizon Telescope collaboration held simultaneous press conferences around the world to reveal the result. The image showed a bright ring with a diameter of about 42 microarcseconds surrounding a dark circular shadow. The ring was brighter on one side than the other, consistent with Doppler boosting from material orbiting the black hole at close to the speed of light. The southern part of the ring appeared brighter because material on that side was moving toward Earth while material on the opposite side moved away. The shadow itself appeared exactly as predicted by general relativity. Its diameter matched calculations based on the black hole's mass estimated from stellar motions. The shape was nearly circular despite the black hole's rotation. The ring of light came from synchrotron radiation produced by electrons spiraling around magnetic field lines in the accretion disk and nearby regions. Photons emitted just outside the event horizon followed curved paths through the warped space-time, some reaching Earth after executing partial orbits around the black hole. This created a photon ring, predicted by theory and now directly observed. The image confirmed several key predictions. The shadow size agreed with the Schwarzschild radius calculated from the black hole's mass, confirming that general relativity correctly describes spacetime even around such extreme objects. The circular shape ruled out alternative theories of gravity that predicted different shadow shapes. The presence of the bright ring demonstrated that hot gas orbits just outside the event horizon exactly as accretion disk theory predicted. Every detail matched what physicists had calculated over decades of theoretical work. Beyond confirming known physics, the image also revealed new information. The asymmetry in the ring's brightness helped constrain the direction of the black hole's rotation axis. The sharpness and clarity of the shadow ruled out possibilities like the black hole being surrounded by material that would blur the boundary. The observations provided the strongest test yet of the no-hair theorem, which states that black holes are completely characterized by just their mass and spin, with no other properties. Following the Messier 87 image, the Event Horizon Telescope team announced in May 2022 that they had also imaged our own galaxy's supermassive black hole, Sagittarius A star. This image was more challenging despite the black hole being much closer, only 26,000 light-years away compared to 55 million for Messier 87. The challenge came from Sagittarius A star's smaller mass. At 4 million solar masses rather than 6.5 billion, it is much smaller and changes much faster. Material orbits it in minutes rather than days, requiring different analysis techniques to combine data. The Sagittarius A star image again showed a bright ring surrounding a dark shadow, this time with an angular size of about 52 microarcseconds. The ring showed clumpy structure, patches of brightness that move and change over the observation period. Despite the dynamic behavior, the average structure matched predictions beautifully. The shadow size confirmed the black hole's mass, and the ring's brightness distribution provided information about the magnetic fields and particle acceleration processes in the immediate vicinity. These images represent milestones in astronomy comparable to the first photographs of planets or the first images of distant galaxies. They transform black holes from theoretical constructs and indirect detections into directly imaged objects. They show that the extreme predictions of general relativity really do describe nature accurately. And they open new possibilities for studying black hole physics in detail, examining the structure of accretion flows, testing alternative theories of gravity, and potentially detecting effects of quantum gravity or new physics beyond Einstein's equations. The photographs of black hole shadows mark the beginning of a new era in black hole astronomy, where these most extreme objects in the universe can be studied not just through their effects, but through direct imaging of the warped space-time around them. Black holes exist throughout the universe in staggering numbers and varieties. From stellar mass black holes formed by collapsing stars to supermassive behemoths at galaxy centers to possible primordial black holes formed in the early universe, these objects play diverse roles in cosmic evolution. Understanding the full population of black holes and their distribution requires combining observations across many wavelengths and detection methods. In our Milky Way galaxy alone, astronomers estimate there may be 100 million stellar mass black holes, the remnants of massive stars that died over the galaxy's 10 billion-year history. Most of these black holes are solitary and invisible dark objects drifting through space with no companion stars or accretion disks to reveal their presence. We have only detected a tiny fraction, mostly those in binary systems where gas from a companion star creates observable radiation. As detection techniques improve, particularly gravitational wave astronomy and microlensing surveys, more of this hidden population will be revealed. The mass distribution of stellar black holes provides clues about how massive stars live and die. The smallest black holes found so far contain about 5 solar masses, consistent with theoretical predictions for the minimum mass needed to overcome neutron degeneracy pressure. The most massive stellar black holes detected through X-ray astronomy contain about 20 solar masses. But gravitational wave detections have found black holes up to 100 solar masses, much heavier than expected from standard stellar evolution theory. These heavy black holes might form in environments with low metal content, where stars can grow more massive before dying, or they might form through mergers of smaller black holes. Between stellar and supermassive black holes lies a mostly unexplored territory called intermediate mass black holes, which would contain hundreds to hundreds of thousands of solar masses. Only a handful of convincing candidates have been found. Some might lurk in the centers of globular clusters, dense balls of stars that orbit galaxies. Others might hide in the outskirts of galaxies, or in dwarf galaxies too small and distant for their central black holes to be easily detected. Intermediate mass black holes are important theoretically because they might represent a transitional stage between stellar and supermassive black holes or a separate formation channel. Supermassive black holes show remarkable diversity despite their common location at galaxy centers. The smallest supermassive black holes contain around 100,000 solar masses and sit in dwarf galaxies. The largest known supermassive black holes exceed 40 billion solar masses, found in the brightest giant elliptical galaxies. The relationship between black hole mass and host galaxy properties suggests they grow together, but the detailed physics of this coevolution remains poorly understood. Do black holes grow primarily through mergers with other black holes, or through gas accretion? How do they regulate star formation in their host galaxies? Observations across cosmic time show that supermassive black holes and their activity have changed dramatically over the universe's history. Quasars were much more common in the early universe, billions of years ago, than they are today. The peak of quasar activity occurred when the universe was about 3 billion years old, roughly 20% of its current age. Since then, the number and luminosity of active galactic nuclei have declined. Most supermassive black holes today are relatively quiet, including the one at our galaxy's center. This evolution reflects changes in gas supply and merger rates as the universe expanded and galaxies evolved. Some of the most distant quasars observed sit more than 13 billion light-years away, seen as they were when the universe was less than 1 billion years old. These early quasars present a puzzle. Their black holes contain billions of solar masses despite the young age of the universe. How did they grow so massive so quickly? Did they form from exceptionally massive seed black holes? Did they experience periods of super-Eddington accretion, growing faster than standard theory predicts? Or does their existence tell us something about the very first generation of stars and black holes? These questions drive observational programs with the most powerful telescopes seeking ever more distant quasars. Black holes also influence their environments on multiple scales. On small scales, the intense radiation and powerful winds from accretion disks can destroy or sculpt nearby structures. On galactic scales, jets and winds driven by active black holes can heat gas, preventing star formation and regulating galaxy growth. On even larger scales, jets from supermassive black holes can extend for millions of light-years, affecting the evolution of entire galaxy clusters. The energy injected by black holes shapes the distribution of matter throughout the universe. Some physicists speculate about exotic types of black holes beyond those confirmed to exist. Primordial black holes might have formed in the very early universe from density fluctuations shortly after the Big Bang. If they exist, they could range from microscopic masses up to thousands of solar masses. Some primordial black holes might even make up part or all of the mysterious dark matter that dominates the universe's mass. Searches have so far found no convincing evidence, but the possibility remains intriguing. Tiny quantum black holes represent another speculative possibility. If extra dimensions of space exist beyond the familiar three, gravity might become strong enough at small scales to create microscopic black holes. Some physicists wondered whether the Large Hadron Collider might create such objects in particle collisions. None have been detected, which places constraints on extra dimension theories, but the search continues. If quantum black holes could be created in laboratories, they would evaporate through Hawking radiation almost instantly, but studying them would provide unprecedented insights into quantum gravity. The diversity of black holes across the universe reflects the diversity of processes that create and grow them. From stellar deaths to galaxy mergers to possibly exotic processes in the early universe, black holes form through multiple channels and then evolve through accretion and mergers over cosmic time. Understanding the full population requires combining observations from radio waves to gamma rays, from individual stars to distant quasars, from gravitational waves to electromagnetic radiation. As observational capabilities continue improving, the sense of black holes becomes more complete, revealing their ubiquity and importance in shaping the cosmos we observe. One of the most important discoveries in modern astrophysics is that black holes and galaxies grow together and influence each other in fundamental ways. Supermassive black holes are not just passive objects sitting at galaxy centers. They actively shape galaxy evolution through feedback processes that regulate star formation and control how galaxies develop over billions of years. Understanding this interplay between black holes and galaxies represents a major frontier in astronomy. The relationship begins with a remarkable correlation discovered in the late 1990s. Astronomers that the mass of a galaxy's central supermassive black hole correlates tightly with the mass and velocity dispersion of stars in the galaxy's central bulge. More massive bulges host more massive black holes, following a relationship that holds across thousands of galaxies spanning a huge range of masses and types. This correlation cannot be coincidental. It implies that black holes and galaxies somehow know about each other, that their growth is coupled through physical processes that maintain the relationship over cosmic time. How does this coupling work? The key lies in feedback, the process by which black holes affect their surroundings. When a supermassive black hole accretes matter, it does not just quietly consume material and grow. Instead, the accretion process is incredibly violent and energetic. Gas falling into the black hole releases gravitational potential energy, heating the accretion disk to millions of degrees. This hot material radiates intensely across the electromagnetic spectrum, particularly in X-rays and ultraviolet light. The radiation pressure can drive powerful winds that blow gas out of the galaxy's center at thousands of kilometers per second. These winds and the radiation itself interact with gas throughout the galaxy, heating it and preventing it from cooling and collapsing to form new stars. Without this heating, gas in galaxies would cool efficiently, settling into dense clouds that would form stars continuously. Galaxies would consume their gas supplies quickly, converting most of their mass into stars within a few billion years. But observations show that star formation in most galaxies proceeds much more slowly, with gas supplies lasting throughout cosmic time. Black hole feedback provides a natural explanation for this reduced efficiency of star formation. Jets by rotating black holes provide another crucial feedback mechanism. These jets carry enormous amounts of energy and momentum, capable of affecting gas far from the black hole itself. When jets plow into surrounding gas, they create shock waves that heat the gas to millions of degrees. They also create bubbles and cavities, pushing gas aside and stirring it like a giant cosmic spoon. Observations of galaxy clusters show numerous examples of these bubbles, visible in X-ray images as cavities in the hot gas surrounding central galaxies. The energy required to create these structures can only come from the central supermassive black hole. The interplay between black holes and star formation creates a self-regulating cycle. When a galaxy contains abundant cold gas, star formation proceeds rapidly and the black hole grows through accretion. As the black hole grows, its feedback becomes stronger, heating more gas and reducing star formation. This reduces the supply of gas available to feed the black hole, causing its activity to decline. With less black hole activity, gas cools and star formation resumes. This cycle repeats over hundreds of millions of years, maintaining a balance between star formation and black hole growth that produces the observed correlations between black hole mass and galaxy properties. Computer simulations of galaxy evolution now routinely include black hole feedback as a crucial ingredient. Without it, simulated galaxies form too many stars too quickly, producing galaxies very different from those observed. Including realistic prescriptions for black hole feedback, based on theoretical understanding of accretion and jets, produces simulated galaxies that match observations much better. These simulations have become essential tools for understanding how galaxies form and evolve from small fluctuations in the early universe to the diverse population of galaxies we see today. Galaxy mergers play a particularly important role in black hole and galaxy coevolution. When two galaxies collide and merge, their gas is violently disturbed, losing angular momentum and falling toward the center. This merger-driven inflow provides abundant fuel for both star formation and black hole growth. Observations show that many of the most luminous quasars and most actively star-forming galaxies are merger systems. The two processes peak together, both triggered by the same influx of gas. Eventually, the black hole feedback becomes strong enough to expel or heat remaining gas, quenching star formation and leaving behind a massive elliptical galaxy, with a dormant supermassive black hole at its center. The central black holes in merging galaxies eventually merge themselves, sinking toward the center of the merged galaxy and forming a binary black hole system. These binaries gradually shrink through interactions with stars and gas, eventually merging in a burst gravitational waves. The space-based gravitational wave detector LISA will observe these mergers directly, providing information about black hole growth and galaxy mergers throughout cosmic history. These observations will test theoretical models of black hole and galaxy coevolution in detail. Despite tremendous progress, many questions remain open. What determines the specific relationship between black hole mass and bulge properties? Why does the same relationship hold across such a wide range of galaxy types? How do black holes in disk galaxies like the Milky Way maintain the correlation when most of the galaxy's mass is in the disk rather than the bulge? What role do black holes play in the formation of the most massive galaxies in the universe? How important are black hole mergers versus gas accretion in growing supermassive black holes over cosmic time? These questions drive ongoing research combining observations theory and simulations to build a complete picture of how black holes shape the universe on the largest scales. Among the deepest mysteries surrounding black holes is the information paradox, a conflict between quantum mechanics and general relativity that has puzzled physicists for decades. The paradox arises from asking what happens to information about matter that falls into a black hole. According to quantum mechanics, information cannot be destroyed. But if a black hole eventually evaporates through Hawking radiation, and that radiation is completely random, where does the information go? This seemingly technical question touches profound issues about the nature of reality and has driven much research in theoretical physics. The paradox begins with a principle called unitarity in quantum mechanics, which states that information is preserved as systems evolve. If you know everything about a quantum system at one time, you can in principle calculate everything about it at any future time. Information may become scrambled and difficult to access, but it is never truly lost. This principle underlies the mathematical consistency of quantum mechanics and has been verified in countless experiments. Violating unitarity would require abandoning fundamental aspects of quantum theory. General relativity suggests that black holes violate this principle. When matter crosses the event horizon, information about that matter seems to disappear from the external universe. An outside observer can never retrieve information about what fell in because nothing can escape from inside the event horizon. As far as the external universe is concerned, the information is gone forever. This loss continues as the black hole consumes more matter over time, steadily accumulating information that becomes inaccessible to outside observers. The situation becomes acute when considering black hole evaporation through Hawking radiation. Hawking showed that black holes radiate thermally, emitting particles with a temperature inversely proportional to the black hole's mass. This radiation carries energy away, causing the black hole to shrink. For stellar mass or supermassive black holes, the evaporation time is enormously long, far longer than the current age of the universe. But eventually, given enough time, any black hole will evaporate completely. What happens to all the information about everything that ever fell in? If the Hawking radiation is truly thermal, meaning it is completely random with no information beyond the temperature, then the information is lost when the black hole evaporates. This would violate quantum mechanics and require fundamentally revising our understanding of physics. Alternatively, the information might somehow be encoded in subtle correlations in the Hawking radiation. The radiation might look thermal but actually contain all the information about what fell in, encoded in correlations too subtle to detect easily. This would preserve unitarity but requires explaining how information deep inside the black hole gets transferred to radiation emitted from near the horizon. Stephen Hawking originally believed information was destroyed, that black holes really did violate quantum mechanics. In 2004, after decades of debate, he conceded that information was probably preserved and proposed that quantum fluctuations at the event horizon might allow information to escape. But his proposal remained incomplete, and many physicists found it unsatisfying. The information paradox has driven research in multiple directions, each attempting to resolve the conflict between quantum mechanics and general relativity. One approach suggests that information is stored at the event horizon itself in subtle modifications to the horizon's structure. The holographic principle, inspired by black hole thermodynamics, proposes that all information in a volume of space can be encoded on its boundary. For black holes, this means information about everything that fell in might be encoded in the structure of the event horizon. As the black hole evaporates, this information gradually transfers to the outgoing Hawking radiation through subtle quantum correlations. Their approach proposes that firewalls exist at event horizons, surfaces of extremely high energy that destroy anything attempting to cross. Firewalls would prevent information from truly entering the black hole interior, resolving the paradox but violating the equivalence principle that says nothing special should happen at the event horizon. This proposal sparked intense debate about whether consistency of quantum mechanics requires giving up the smoothness of space-time predicted by general relativity. String theory offers potential resolution through the idea that black holes are actually complex quantum objects with enormous numbers of internal states. The entropy of a black hole, proportional to its event horizon area, reflects this vast number of possible internal configurations. In this view, black holes are not simple objects characterized only by mass and spin, but are instead rich quantum systems capable of storing and processing information. The Hawking radiation would then reflect the black hole's internal state, preserving information in principle, even if extracting it is incredibly difficult in practice. More recent work has focused on understanding how information escapes through careful quantum mechanical analysis of the radiation process. Physicists have shown that quantum entanglement between particles inside and outside the black hole plays a crucial role. The information may escape through subtle correlations between different parts of the Hawking radiation, correlations that only become apparent when analyzing the radiation's quantum state in detail. These calculations suggest information does escape, but in ways so scrambled that reconstructing what fell in would be extraordinarily difficult even in principle. The information paradox remains unsolved despite decades of intensive research. Different approaches make different assumptions and reach different conclusions about how information escapes or whether general relativity needs modification. The paradox highlights a deep incompatibility between quantum mechanics and general relativity, two theories that work beautifully in their own domains but clash when brought together in extreme circumstances. Resolving the paradox will likely require a complete theory of quantum gravity, something physicists have sought for nearly a century without success. The black hole information paradox is not just an abstract puzzle for theorists. It touches fundamental questions about the nature of space and time, the fate of information in the universe, and whether reality is fundamentally deterministic or allows true randomness and loss of information. It drives research in string theory, loop quantum gravity, and other approaches to quantum gravity. And it reminds us that despite tremendous progress in understanding black holes, the deepest questions about these objects remain unanswered, pointing toward physics beyond our current theories. Beyond their scientific importance, black holes have captured the public imagination like few other scientific concepts. They appear frequently in science fiction, popular science books, movies, and television shows. This cultural presence reflects both the inherent drama of black holes and humanity's fascination with extreme phenomena and the unknown. The portrayal of black holes in popular culture has evolved alongside scientific understanding, sometimes inspiring research and often helping communicate complex ideas to broad audiences. Science fiction writers embraced black holes quickly after the term was coined in the late 1960s. They offered dramatic plot possibilities for stories about space exploration and cosmic catastrophes. Early stories often treated black holes primarily as dangers to avoid cosmic whirlpools that would destroy spaceships foolish enough to approach. As scientific understanding deepened, stories became more sophisticated, exploring ideas like time dilation near event horizons, the use of black holes for space travel through hypothetical wormholes, or even extracting energy from rotating black holes through the Penrose process. One influential early depiction appeared in the 1979 Disney movie, The Black Hole, which showed a research vessel encountering a massive black hole at the edge of explored space. While the movie took considerable artistic license with the physics, it brought black holes into mainstream popular consciousness and inspired many young viewers to learn more about real black hole science. The visual design showing a glowing accretion disk around the dark void anticipated later scientific visualizations of black holes. The 1997 science fiction film Contact, based on Carl Sagan's novel, depicted a more scientifically grounded approach to extreme space-time. While focusing on wormholes rather than black holes proper, it showed scientifically accurate visualizations created in consultation with physicist Kip Thorne. This attention to scientific accuracy helped establish expectations that science fiction could be both dramatically compelling and faithful to real physics. The 2014 film Interstellar raised the bar for accurate scientific visualization in popular media. Director Christopher Nolan worked closely with Kip Thorne to ensure the black hole depicted, called Gargantua, looked as realistic as possible given current understanding of black hole physics. A team of visual effects artists wrote new rendering software based on general relativistic ray tracing, calculating exactly how light near a massive rotating black hole. The resulting imagery showed features like gravitational lensing, the photon sphere, and asymmetric brightness of the accretion disk due to Doppler effects. Interstellar's depiction of Gargantua was so sophisticated that it inspired actual scientific papers. The visualization showed multiple light rings around the black hole created by photons that had orbited partially around the black hole before reaching the camera. These features had been predicted theoretically but never visualized so realistically. Scientists studying the visual effects found new details about how black holes would actually appear to observers at various positions and angles. The film demonstrated how popular media could contribute to scientific understanding while reaching audiences of millions. Popular science books have played a crucial role in communicating black hole science to general audiences. Stephen Hawking's A Brief History of Time became an international bestseller in 1988, introducing millions of readers to black holes, the Big Bang, and modern cosmology. Though famously difficult to read despite Hawking's attempts at accessibility, the book showed enormous public appetite for understanding the universe's deepest mysteries. Later popular science books by authors like Kip Thorne, Brian Greene, and Neil deGrasse Tyson continued making black hole physics accessible to non-scientists. Documentaries and television series have brought black hole science to even wider audiences. Programs like Cosmos, both Carl Sagan's original 1980s series and Neil deGrasse Tyson's 2014 revival, included segments explaining black holes with state-of-the-art visualizations. The Event Horizon Telescope's 2019 release of the first black hole image generated enormous media coverage worldwide, appearing on news programs and front pages and inspiring countless articles, videos, and explanations aimed at general audiences. Black holes have also entered everyday language and metaphor. People describe anything that consumes without returning as a black hole, from financial losses to time-wasting activities. This metaphorical use reflects black holes' cultural status as ultimate consumers, the cosmic garbage disposals that swallow everything and give nothing back. While the metaphor oversimplifies the science, ignoring phenomena like Hawking radiation and jets, it captures something essential about public perception of black holes as exotic and extreme. Educational planetarium shows frequently feature black holes, using immersive projection technology to give viewers the feeling of approaching these extreme objects. Virtual reality experiences allow users to fall into black holes or orbit near event horizons, seeing gravitational lensing and time dilation effects in simulated environments. These experiences help make physics concepts tangible and memorable, inspiring future scientists and satisfying public curiosity about cosmic extremes. The portrayal of black holes in popular culture has generally improved in scientific accuracy over time, reflecting both advances in understanding and growing appreciation for getting the science right. Modern science fiction writers often consult with scientists to ensure their depictions are plausible. Filmmakers hire scientific consultants and create sophisticated visualizations based on genuine physics calculations. This raises the standard for scientific accuracy in entertainment, while acknowledging that dramatic needs sometimes require bending or simplifying the science. This cultural presence serves multiple purposes. It helps communicate scientific discoveries to broad audiences, building public support for research and inspiring young people to pursue science careers. It shows that cutting-edge physics can be exciting and relevant to non-specialists. And it reflects deeper human tendencies to wonder about extreme phenomena, to imagine what lies beyond familiar experience, and to seek understanding of nature's most dramatic manifestations. Black holes in popular culture bridge the divide between specialized scientific research and universal human curiosity about the cosmos.